Today we're going to be looking at partition coefficient. Okay, and to understand partition coefficient, we're going to look at an example. So let's say that I have a beaker. Okay, and in this beaker, what I have is I have aqueous iodine. Okay, I have aqueous iodine, and what I want to do is I want to separate the iodine from the water into an organic solvent. Okay, I want to separate the iodine from the water and I want to extract it into an organic solvent. Okay, so what I'm going to do is I'm going to take this iodine. So I'm going to take this aqueous iodine. I'm going to put it into a separating funnel. Okay, right. I'm going to put it into a separating funnel. Right. So what I've done is I have iodine in the aqueous layer here, and I want to extract this iodine. I want to extract this iodine into hexane. Okay, so that will be my organic solvent. Okay, so what I'm going to do is I'm going to add hexane. Okay, I'm going to add hexane, and over here I have, obviously, the separating funnel is closed over here, right? And what I'm going to do is I'm going to mix the two together. So what I'm going to do is I'm going to put the lid. I'm going to put the lid on this funnel. Okay, I'm going to cover it. Okay, I'm going to shake the two layers. Okay, shake and mix, right? And then I'm going to allow gas to escape. Okay, and what I end up with over here is the following. Okay, I allow the gas to escape, right? And now what I have is right, I have the aqueous layer and I have the hexane layer. And what's happened is that some of the iodine has been extracted from the aqueous layer into the hexane layer. Now what I'm going to do next over here is that I'm going to open the tap. Okay, I'm going to open the tap and then allow the I'm going to open the tap. Okay, and I'm going to extract the aqueous layer. Okay, I'm going to extract the aqueous layer here, and in the funnel now, what do I have left over? I have the iodine in the hexane. So in the funnel I have the iodine in the hexane. So what I've done is I've essentially separated some of the iodine from the aqueous layer into the organic solvent. I've separated some of the iodine from the aqueous layer into the organic solvent. Okay, if you want to look at a more detailed diagram, you can just look at your notes. Okay, this diagram in more detail in terms of what we're doing is shown in the notes. Now to understand what's happening here, let's just look at the same iodine in a beaker again. Okay, so here we have aqueous iodine in a beaker. Okay, and I'm going to use this to represent the aqueous iodine, right? So this is my solute. Right? This is my solute, iodine aqueous, right? And what I'm doing here is I'm adding hexane. Now initially what happens is, right, these iodine particles are moving around, right? And initially what happens is that these iodine particles start moving into the hexane layer. And as they start moving into the hexane layer, at the same time, of course, simultaneously some iodine particles will be moving back from the hexane layer into the aqueous layer, right? Eventually what happens is, right, eventually the rate at which the iodine particles are moving into the hexane layer is equal to the rate at which they're moving back into the aqueous layer. Eventually the rate at which the iodine initially all the iodine was in aqueous solution, it was in water, right? So when we look at probabilistically, right, there's only one way the iodine can go. Initially it'll just move from water to hexane, but obviously over time the concentration in hexane will also begin to increase, so the rate at which the iodine is going back into the aqueous layer is increasing. Eventually what happens is that the rate at which the iodine is moving from the aqueous layer into the hexane is equal to the rate at which it's moving from the hexane back into the aqueous layer. Okay, so here what we have is we have dynamic equilibrium, right? Right, right. Initially, the iodine is simply moving into the hexane layer. Eventually, the rate at which it's moving into the hexane is equal to the rate at which it's moving. So at this point, what we have is we have a dynamic equilibrium, right? The rate of the forward reaction is equal to the rate of the backward process here, right? The rate at which iodine moves into hexane is equal to the rate at which it moves back from hexane into the aqueous layer. And the ratio of their concentrations at this point, the ratio of their concentrations at this point is known as the partition coefficient, okay? That is the ratio of the concentration of iodine in hexane to the concentration of iodine in the aqueous layer. So the partition coefficient can be defined as the following. Okay. The partition coefficient, okay, we use the abbreviation KPC, right? PC stands for partition coefficient, is defined as the ratio of the concentrations of a solute in two immiscible solvents. These two solvents do not mix with each other, okay? Immiscible solvents at equilibrium. Obviously, this equilibrium will be at a given temperature, right? Because if you change the temperature, then obviously you're going to change the value of the equilibrium constant. So if you go back to this particular example here, right, we had hexane and water as our two immiscible solvents, and we said that the ratio of the concentration of the solute, in this case iodine, in these two immiscible solvents, right, at equilibrium is the partition coefficient, right? And right, the greater the partition coefficient, the more soluble it is in the hexane relative to water, right? Now in this particular example, what I want to know is, what do you expect the value of partition coefficient to be? Do we expect it to be greater than 1 or less than 1? Here we expect the partition coefficient to be greater than 1 because iodine is more soluble in hexane than in water. Okay, it is more soluble in hexane than in water. And the reason why is because iodine is a non-polar molecule, so it will be more soluble in non-polar solvents such as hexane as opposed to polar solvents such as water. So now let's solve the following question. So the question says, a solution of 5 grams of an organic compound X in 50 centimeter cube of water is shaken with 100 centimeter cube of ether. Okay, that's our organic solvent here. After separation, the aqueous solution is found to contain 0.8 grams of X. Find the partition coefficient of X between ether and water. So over here we have the following equilibrium. We have X that is being extracted from the aqueous layer into the ether, right? Ether is our organic solvent, and we know that the partition coefficient, by convention, normally what we do is we extract our solute from water into organic solvents. Okay, in most cases our solutes are found in aqueous layers and we extract them into organic solvents. So by convention, the concentration in the organic solvent is written in the numerator and the concentration in the aqueous layer is written in the denominator. There will be cases where that's not the case, but in most cases this is how we write it. Now initially we know that our mass of X total is 5.00 grams. Okay, that's our initial mass of X. And we said that after extraction, right, the mass of X left in the aqueous layer is 0.80 grams. So that means that in the ether we have 4.20 grams left, right? Because initially we had 5 grams of X in water and 4.2 grams were extracted into the ether, right? That's why we have 0.80 left in the water after the extraction. We have this much left in the water from the initial 5 grams. So that means that 5 minus 0.8, that is 4.20 grams, were extracted into the ether. So these masses are the amounts present at equilibrium between the two, for the solute between the two solutions. So then we can say that our partition coefficient, right, we don't know what X is, but we don't have to convert the concentration into moles per decimeter cube. Since we're taking a ratio, right, doesn't matter what units we're using as long as they're the same in the numerator and the denominator. So we'll just use our units as grams per centimeter cube for concentration, okay, mass per unit volume. Since the data given to us is in grams and centimeter cube, we can directly use those units as long as they're the same for numerator and denominator. So we can say our partition coefficient here is equal to the concentration in ether, that is 4.20 grams per, we have a volume of 100 cm cube. So we have 4.20 divided by 100 divided by 0.8 grams, and we have 50 cm cube of water, right? So in that 50 cm cube, we have 0.8 grams left over. So we can say P is equal to 50 cm cube. So 4.20 divided by 100, that's the concentration in ether, divided by 0.80 divided by 50. That's the concentration in water. So the partition coefficient here comes out to 2.625. Okay. So what this partition coefficient means is that X is 2.625 times more soluble in ether than it is in water. The next question that we have says, when 100 cm cube of an aqueous solution containing 2 grams of an organic dye X is shaken with 20 cm cube of hexane, it was found that 1.6 grams of the dye had been extracted into the hexane. What we want to do is we want to find, part A says find the partition coefficient, find the KPC partition coefficient of X between hexane and water. Here we have the following equilibrium. We have X in the aqueous layer in equilibrium with X in hexane. So our partition coefficient is the ratio of the concentration of X in hexane and X in aqueous solvent, right, or water. Now again, the initial mass of X is 2.0 grams, right? After the extraction, we have mass of X in hexane is equal to 1.6 grams, and the volume is 20 cm cube. So therefore, from the 2 grams, 1.6 grams were extracted into the hexane. So the remaining 0.4 grams are in the aqueous layer, right? So that is 0.4 grams. The volume was 100 centimeter cube. So again, we'll just use our concentration. We're going to use grams per centimeter cube for our units of concentration, right? Since we just want to take the ratio, we can say that KPC is equal to the concentration of X in hexane, that's 1.6 grams per 20 cm cube, divided by the concentration in water, that's 0.4 grams per 100 cm cube. So here the partition coefficient comes out to 20. Okay, so that's your answer for part A. Now the next part of the question says, that's part B, find the minimum volume of hexane needed to ensure that less than 0.1 grams are remaining in the aqueous layer. Now the question is saying, if you had the same 100 cm cube aqueous solution, right, what volume of hexane would you need instead of 20 cm cube? What volume would you need to ensure that only 0.1 grams are left over in the aqueous layer, whereas the rest has been extracted? So over here, again, we know the KPC, right? That is the concentration of X in hexane divided by the concentration of X in the aqueous layer. Now over here, we know that the initial amount of X that we have is the same. We have 2 grams, right? And we have the same aqueous layer, right? But in the aqueous layer, our mass is now left over after the extraction is 0.1 grams, right? And we had 100 cm cube of aqueous solution, right? Whereas the mass of X Where is the mass of X in hexane? We need is going to be 1.9 grams, right? From the 2 grams, you want to ensure that only 0.1 grams are left over in the aqueous layer. That means 1.9 grams will be extracted into the hexane, and the volume is what we have to find. Now again, we're going to take our concentrations as grams per centimeter cube. We found out the partition coefficient in the previous part, that was equal to 20, right? The concentration in hexane is 1.9 grams per V centimeter cube. The concentration in the aqueous layer is 0.1 divided by 100. Now usually it's easy to make a mistake when you have a fraction of fractions, right? If you want to solve this step by step, just treat this entire fraction as the denominator, this entire fraction as the numerator. So you just multiply 0.1 over 100 on both sides. You get 20 times 0.1 over 100 is equal to 1.9 over V. So here you get 0.02, multiply V on both sides, you have 0.02 V is equal to 1.9. This gives us V as 95 centimeter cube. So that is our answer. Okay.